we know that a function y equal to f of x, when we differentiate it, we got f prime of x. And that's called the derivative of this function f, which is a new function derived from this function f over here. So y prime is equal to f prime of x. So this process of calculating derivative using this limit of this quotient over here is called differentiation. So we have different notation for this derivative of this function. So we can use f prime of x, or we can put y prime. We can also call this dy dx, or df dx, or this one over here, or this one over here, and this one over here. So the most common one, the two most common one will be this two. Actually, the three most common one will be this three over here. Now, when you use this notation, dy dx over here, you read this as dy dx. Differentiate y with respect to x. Now, this d dx over here is called the differentiation operator. In Chinese, we call that 微分因子. Okay. Now, the d over here, actually, this notation, this differentiation operator, kind of makes sense. Think about, remember, the derivative is the limit of this quotient, right? So as delta x approaching to 0, so the delta here stands for the change in y over change in x. So it is the limit of this average rate of change. Now delta start with a d, so as this delta x approaching to 0, then you're going to replace this delta and delta here by the d here. So dy dx. Okay, you see the relation between this two, this notation and this, right? Okay. So this is called the differentiation operator. Okay. Now we call that a function is continuous at a. If you look at the graph, then you see there's no break at this a over here. And the definition, the function is continuous at a is when you take the limit of this function as x approaching to a, that will be equal to f of a. That means you can direct substitute a into this function and to find this limit. Now, what about differentiable? Differentiable at a, that means the derivative exists at a as a real number, okay? Now, because the derivative corresponds to the slope. So the slope of the tangent line exists. Now, notice that to be differentiable, the function had to be continuous at a first. Otherwise, there's no tangent at a. So differentiable require continuous, okay? So differentiable at a require the function to be continuous at a. But continuous at a doesn't imply differentiable at a. Okay, we'll see. I'm going to give you one example later on. Okay. Now, f prime of a, you can write this as dy dx and put a bar over here, x equal to a, which means you evaluate this dy dx when x equal to a. So this, you can think about that as evaluate at x equal to a. So you think about this as the slope of the tangent at a. So definition, a function f is differentiable at a if f prime of a exists. It is differentiable on an open interval a to b or any one of this if it is differentiable at every number in the interval. Okay. Example 5. Where is the function f of x equal to absolute value of x differentiable? Now, to be differentiable means the derivative exists or the slope of the tangent exists, right? So let's graph this absolute value function. So we remember it is the V shape, right? Okay. So now at the left side of this zero over here, you see the slope of the tangent or the slope of the graph is equal to -1. And on the other side of the 0 over here, the slope is going to equal to positive 1. So the function will be differentiable when x is less than 0 and also when x is greater than 0, because the slope of the tangent exists as a real number. Now what about at 0? So let's find f prime of 0. By definition, it's the limit of this quotient as h approaching the 0. F of 0 plus h, we're going to substitute h into this x over here. So that will be absolute value of 0 plus h. And f of 0 is going to be just 0. Simplify this is the limit of this absolute value of h over h. Now notice that absolute value of h equal to 0 when h equal to 0, which is exactly at this number over here. So we need to consider the left and the right hand limit in order to find this two-sided limit here. So let's look at the right hand limit here. As h approaching the 0 from the right, absolute value of h when h is approaching 0 from the right, h will be greater than 0. So absolute value of h is going to be equal to h. So we can just remove this absolute value and then become just h over here. H over h is just 1. Limit of 1 will be equal to just 1. So the right hand limit for this is going to be 1. What about the left hand limit? For the left hand limit over here, h is going to approaching 0 from the left. So h is going to be less than 0. So when h is less than 0, absolute value of h will be equal to the opposite of h. So that we're going to replace this absolute value h by negative h over here. Simplify, we're going to get negative 1. The limit of negative 1 is negative 1. So we found that the left hand limit of this is negative 1. Now, since the left hand limit and the right hand limit are different, so f prime of 0 does not exist. So the function is not differentiable at 0, but it is differentiable everywhere else. So 0 is the only number that the function is not differentiable at. Now let's try to find the formula for the duality of this function f. Well, when x is less than 0, you see the slope of the tangent, it is negative 1. So f prime of x equals negative 1. When x is greater than 0, the slope of the tangent is positive 1. So that's equal to 1 when x is greater than 0. And when x equals 0, the duality does not exist. So f prime does not exist at 0. So the graph of this, so this is the function f prime of x. So if you graph this function, it's a piecewise defined function. So when x is greater than 0, it is equal to 1, so it's here. When x is less than 0, it is equal to negative 1, so here. When x equals 0, the function does not exist. So you see this is an open gap over here. You see this is an open gap, and this is an open gap right here. So it's open circle here, and over here.